Hello. Last time we arrived at this picture which visualizes similarity classes. So these small segments indicate similarity classes. For example, S and T would be in different similarity classes. And I raised a question whether each class might have a representative matrix that is in diagonal form. Or in other words, is every matrix similar to some diagonal matrix? And I already indicated that the answer is unfortunately perhaps no. And today we are looking a bit closer at this issue. We call a transformation diagonalizable if it has a diagonal representation with respect to some basis. We will always use the same basis for the codomain as for the domain. And a diagonalizable matrix is one that is similar to a diagonal matrix. Here's an example. So this matrix is diagonalizable because if you take this non-singular matrix, which has this inverse, then multiplying these three matrices gives us a diagonal matrix. A diagonal matrix has some diagonal elements, like those that I'm indicating, and all other elements are zero. Now, this matrix is not diagonalizable, and here the argument is a bit more sophisticated. It's based on the observation that n squared, so n times itself, is equal to the zero matrix. Now the argument on the slide is in terms of maps, which is good, but perhaps now it's easier to follow along if I give you a direct argument based on just matrices. So the argument is, suppose for a contradiction that there exists a diagonal matrix D such that there is a non-singular matrix P, and P times N times P inverse would be equal to that diagonal matrix. So let's suppose for a contradiction that such a diagonal matrix exists. So now we take the square of both sides. And then we have Pn, P inverse, Pn, P inverse. Now P inverse P is the identity matrix. And now we have Pn squared P inverse. And n squared is zero, as I've mentioned before. So on the right hand side, actually, we have the zero matrix Z. Now, if we look at this equation, d squared is equal to the zero matrix. Well, the diagonal matrix squared, well, if you square a diagonal matrix, I think you'll find it easy, or maybe you are already aware of this fact that you can simply square the diagonal elements. So this matrix then would be equal to the zero matrix, which of course implies that D1 and D2 are both zero, where D1 and D2 are the diagonal elements of this supposed diagonal matrix. So we have derived that if n is diagonalizable, then it would be similar to the zero matrix. But we know from the last video that the only matrix that is similar to the zero matrix is the zero matrix itself. But n is not the zero matrix, clearly. So we have a contradiction to our assumption that there is a diagonal matrix D that satisfies this equality. Do read this argument in terms of maps, which is in some sense perhaps slightly more elegant. We have now this lemma, which is basically a restatement of what it means for a transformation to be diagonalizable. So let's maybe look at that again. So it said a transformation is diagonalizable if it has a diagonal representation, so that's a matrix, with respect to some basis. And now the lemma says a transformation T is diagonalizable if and only if there's a basis B such that T, the transformation applied to a basis element, is a multiple of that same basis element. That's basically a restatement of the definition, but let's look at it in slightly more detail. So a transformation T was diagonalizable. That meant it has a diagonal matrix as representation with respect to some basis. So here you have it, the diagonal matrix. But you know how this is constructed here, this matrix. It's constructed by running the basis elements through the transformation and then representing the result with respect to the basis. So this is how these columns are obtained. So here we have these columns. And let's focus on the first column, but the others will of course be similar. So we can write this as lambda 1 times 1, 0, and then only zeros. And this is equal to lambda 1 times the representation with respect to B of the first basis element. And now we have it. So why? Because here we have T of beta 1, and here we have lambda times beta 1. Well, both vectors are in the representation with respect to some basis B, but that doesn't matter actually. So we have, so to speak, derived this, but of course it followed almost immediately from the definitions. So this was strictly speaking if and only if, but the converse direction is perhaps even simpler. This matrix here is not diagonal, but we can try to find a diagonal matrix similar to it by finding an appropriate basis. So we can take the following view. We say that capital T is the representation of a transformation with respect to the standard basis. So then that's the top part of the arrow diagram. And now we will find a basis, another basis, B, with respect to which the transformation T has a diagonal representation. So that's the thing at the bottom here. Okay, and that means now using the lemma, this lemma here, with respect to this lemma, we have to find basis elements beta 1, beta 2, and scalars lambda 1, lambda 2, such that we have these equations. So multiplying the matrix to the basis element should give us a multiple, a scalar multiple of that same basis element. And we have to find two different, in fact, linearly independent vectors, beta 1, beta 2, and scalars lambda 1, lambda 2. Well, lambda 1 could be equal to lambda 2 as far as we know, such that these equations hold. Now, either of these equations has essentially this form here. Well, it looks a bit like a linear system, except that it's strictly speaking not linear because x is an unknown and B1 is also an unknown, so we are really multiplying two variables, which is something that we don't do in linear systems. We can still write it in this way. And now if we imagine that x is a parameter, then we have a linear system. So for any fixed x, for any number x, we have a linear system down there. Now this linear system would be a homogeneous system, so clearly a solution would be the zero vector, i.e. b1 and b2 equal to 0, gives us a solution no matter what. But of course that's a solution that we are not interested in, because we want basis elements beta 1, beta 2, and we can't use the zero vector in any basis. So that's not a good solution for us. In fact, if we just choose a random x, then usually that system will only have one solution, namely the trivial one. So we have to sort of choose very specific x to generate more solutions. One way of doing it is to produce a zero here. This would be choosing lambda, well, or x equals -1. This might be then lambda 1 equals -1. Because then here we have 0, and then 0 times b2 equals 0, equals 0. So that's 0 equals 0, we can just omit it. Now here we would have 4 minus -1 times b1, that's 5 b1 plus b2 equals 0. And that gives us now a whole line of solutions, this line here. So there we find non-zero solutions. Okay, so we might use this lambda 1 -1, and as beta 1 we might take some point, not the origin, on that line. And then another way of generating an interesting solution would be x equals 4, or lambda 2 equals 4. That gives us a 0 here. Then here -1 minus 4 is -5 times b2 equals 0. Well, that forces b2 to be 0. And then the first line is also true. And in fact, the equation system is true then for all b1. So again, we have a full line as the solution. And we can pick lambda 2 to be 4. And as beta 2, we will pick some point on that line, again, not the origin. And then here we go. So we have now found that the original matrix, which was not diagonal, is diagonalizable to D. So it's similar to this diagonal matrix, and that would be the basis